Thank you, Nathan. And yeah, welcome everyone, and thanks for joining me today into this final webinar about IBM Quantum. What we will talk today is more or less a small introduction as a recap about quantum. We will do quantum together, and you will see what are the potential applications for quantum and how quantum can helps and contribute in solving out different problems in the world, especially what is IBM is doing. So mainly it's our mission to bring useful quantum computing to the world. It's not about bringing up a new technology that's going to replace everything, but it's also going to be integrated with the current technologies that we have in the world, like the AI, the high performance computing, in a useful way that we not only innovate or like excited about quantum computing, but we see actual and productive results. And this is could be projected in our maybe classical computation theory problems that we have mainly two types of problems so far in the classical world. The one which we will call it polynomial or like the easy problems and the hard problems, which are NP. And we already know that the easy problems or like those polynomial one are the one who can be solved by the classical computers in different methods or like in different approaches, starting from brute force algorithm, doing some simulation and approximation solutions, or even using the AI to solve out these problems. But however, we have also the bigger type of problems in our problem space, which we will call them NP. These NP problems are not tractable, I would say, by the classical computers. What does that mean? It means that it may need a lot of time for the classical computers to solve out these problems, or it needs a large amount of data. It's not about only the timing. Even if you get the timing and the size, can the classical computer produce out the correct result? Is there, or like, can the algorithm that we use by the classical computers to solve this problem 100%? Well, this is the actual world, or like, this is what is currently doing in the classical computers. But then we have the quantum computers come in here and plays a vital role in extending our solution space from not only the easy problems, but we were able to extend it since the quantum computers are able to solve out more of these problems. Not only that, we are also able to explore new use cases that the quantum computers are be able to solve. And this is translated into different use cases in cross industries, starting out from developing materials. We are now trying to develop some sustainable materials regarding the batteries, for example, for electric vehicles, or like the making out some smart ways by designing the storage in order to reduce out the space. Also, materials that is related, for example, to be planes. We are looking to reduce lighter things with less cost and less pollution to have more sustainable usage of them. And for example, planes and flying is one of the most interesting use cases. Also, since we have or like we are now dealing in the quantum world with small particles and small atoms, we were able to simulate the behavior of the molecules and the and the small particles here in the world by uh, discovering new classes, for example, of antibiotics or trying to do something in the medical engineering. Also, this is also important for designing some superconductors for electromobility and renewable energies. This is not only in the manufacturing and research part, we have also mainly solving out complex equations in the algebra space. Has many use cases by, for example, the finance, when we solve out optimization or like some equations related to the risk portfolio to trying to optimize the profit that we have or like even increase it. Also, for example, in the logistic, when I'm able to calculate or like to get the optimum vehicle route through our super popular problem to traveling salesman, this is also a challenge for us. So, and also, for example, detecting patterns in a hard or like in a complex structure of the data itself and doing some more or less data analysis. So these problems has mainly a complex structure that the classical computers are not able to, let's say, uh, split it out in order to solve out the problems. But it also, so therefore we need the quantum computers. So since this is the final webinar, I would like maybe to ask a question this way, but about what is quantum computing. But let's say if we have a scala of from 1 to 5, which is 1 very bad, 5 very good, how would you be able to explain after this 2 weeks of Qiskit Fall Fest, how to explain the quantum technology or like the quantum computing concept to a 5 years old kid? Maybe you can write in the chat and I can see some um, feedbacks from you or comments. Would you be able to do it? Okay. And we have Philip, which said, okay, I have a 3. Someone else, maybe. 4. We have Tim. Okay. That's so cool. Okay. Great. So most of us are now already familiar, I would say, with the quantum computing concepts, that they are based on the phenomenons of quantum mechanics. So far that we are dealing with the classical states and the classical physics, which describe everything in type of 2 states or like 2 electric states, which is 0 or 1. But here we're going to use the phenomenon from quantum mechanics, which are the superposition, entanglement, and interference, in order to process out the information in our computers. So it's not our goal, let's say, to explain or to dive deeper in the quantum physics and solve out the or like try to describe these behavior more or less, than using them to process information and through the arithmetic units that we have. The superposition mainly says or like it's a state that a quantum system can exist in 2 states, like a combination of 2 states, instead of being existing in determinedly in a determined way in one of these states only. But here we can mix or like have a mix between them in an easy word. Entanglement said or like states that quantum system could share information between each other, so we can infer or like determine or like interpret some information about the other system when we observe one of the other system. The interference is more or less important, that we can affect the behavior of the quantum parts or like the parts of the quantum system in order to get out the likelihood solution, or like that I have a set of solutions and I would like to let the perfect or like the optimal solution show him the cells by doing out some effects and making out some interference. Well, why I need quantum, or like why I reach out a point and I said, let's explore quantum computers. Because due to the Moore's law, we know that the number of transistors in a classical circuit was doubling about every 2 years. But now we are approaching a kind of limit that we are not able to improve the physical hardware anymore as quick and as fast as we were in the past. And therefore, the classical physics or like the classical hardware are reaching out their limits. Even more if we said, okay, I have these quantum physics phenomenon, let me simulate this in a classical computer. Like we can simulate now different type of physics phenomenon like heat, like temperature, or like winds, or like different kind of interactions between molecules. Let me use these concepts and simulate it in a classical computer. Well, at approximately 100 qubit scale, we found out that even the classical hardwares can no longer simulate what we want exactly, or like what we want to do with the quantum computers. So even at this point, the classical computers are reaching out the limit. So far, the word is encoded into bits. Like for decades, we are trying to encode everything and present everything in the computing world with 1 and zeros. everything like an image, a number, a string, any type of information will be formed to this way. But this is not only about one and zeros. Like the future needs more because we saw that we'll reach out some limitations about this type of presenting information in the world. So like in a simple word, a bit, let's say, is an object that it could be, or like we will represent it as the basic unit of information in our computers, and it could have only two values, like 0 or 1. And there's the operation, which is the logical gate, which can let us apply operations on these units. So it could be the AND, it could be the OR, of two bits, or like it could be flipping one bit value and so on. In the qubit world, or like in the quantum world, is a little bit different. Here, the quantum bit, which is the basic unit of information, it's not only presented as one value, it's presented as a combination of these values. What does that mean? Like, it means that this unit of information can hold out information about the two states in a combinational way. And therefore, I'm not able to use the classical gates. I need to use out something called the quantum gate, which are able to deal out with the new structure of this unit information. So maybe to make it easier, we will assume that this is the space where our qubit is moving around, and it could have a probability of being here, or like being left, or being right, or being at 0, or being at 1. So it's always been moving. And I will describe it mathematically, as I said, here in a kind of equation, like a linear equation would say it's, okay, this is the state 0, and this is the state 1. I would put out here a linear scale, which is B and A, and this means that the qubit is currently in a probability of A, of the power of A for the state of 0, and the power of B in state of 1. And I know, like, but you say you're gonna say, okay, I have now them in a kind of combination. It's moving around so quickly, but for me, as someone who needs to process out the information, I need to know a final word. I need to know the final value of it. That's why I need something called measurement. The measurement is basically taking out a snapshot of this qubit that is moving very quickly around the sphere, and then I will get at the results with a probability way. That with the power of A, I would get out the measurement, or like the value of 0, or I would get out something with a probability of power of B, the state of 1. So it's kind of make a random. So I'm not very sure, as in a classical way, what value I might get. And this is what is exciting about quantum, and we'll see how we can benefit from this kind of things. And now I wanted to apply some gates, or like to apply some information. Let us introduce the X gate. The X gate is basically a flipping around. So if I have let's say a bit on the state of 0, and I will gonna flip it in the classical way, so it's gonna have this the state of 1. Similarly here, we flip out, if I have a superposition of these two states, what I'm gonna do is basically flipping out these linear scales from A to the state of the 0 plus B to the state of the 1. This would be that B would have, or like would be associated with the state of 0, and A with the state of 1, which means that after doing the measurement, I'm gonna get out the probabilities in a vice way. That the power of B would be the probability of getting 0 in the end, and the power of A would be the probability of getting the value of 1. And if we have that, for example, if I'm having not a superposition, if I'm having here only a determined state, which is in the classical way, then for example here the B would be the 0 and the A would be the 1. And if I flip it, then I'm gonna get, with 100% probability, I'm gonna get the value of 1. How I be able to turn out information from the classical way, from 0 or 1, to the combination of them. This can be done doing or like applying the Hadamard operation, which we will do it here in the operation of H to the Hadamard. And this basically maps or like take out a value or like a state in a classical determined way, for example, here to 0, and put it out in a superposition state of two things, which is the state of 0 and 1, and in an equal way. So it means it would have the probability of half getting out 0 and probability of half as well to get out the value of 1. And this is what we have the quantum randomness. So when I apply the Hadamard operation, I'm able to get out the superposition. But like now, okay, I am now dealing with a new structure. I need to represent it in a different way because it's not about only the numbers. Here I need to turn out everything into vectors. So now the state of 0, it's not only the value of 0 itself, but it's also a vector that presents that for the first state, I'm having a positive value, which I will deal it with 1, and with the second value, which would be the 1, I have a negative value. The same thing for the 1, which has the other values. For the first state, which is the original 0 or like the classical 0, I have a negative value, and for the second value, which is classical 1, I would have a positive value. And in this way, I can write it, the linear, or like the equation, I could write it in a linear equation form, where I have A and B are scalars, they could be complex numbers, by the way. And here that 0 and 1, they are not only values of themselves, they are now vectors. And we will call them that like the ket 0, this is the ket 0, and this is the ket 1. And these are the basics in our quantum computing world. It's also important to define when our two quantum states are equivalent. So if I have, let's say, an equation here, which is the A with the state of 0 and plus of the state of 1, and these are the complex numbers where they fulfill the probability rule that the sum of all these probabilities should be equal to 1. And then I'm going to define that two quantum states are equivalent only if they differ by a constant multiple, like the u, where the norm of this u equals 1. And why is that? Because if I have this here, the equation itself, which is a, the power of a plus the power of b, then I could, like, since I have the norm of 1, then it's basically here, if I multiply it with here and then get out the power of u, which should be equals to 1 due to the norm rule, this will not affect the rule here that the sum of the probabilities would be equal to 1. But this is my question maybe to everybody. Uh, should be the norm here, or like why the norm must be equal 1, like must be a constant multiple by u, and its norm should be 1. Why? I don't know. Maybe we would have it in a 5 or a 4. Who knows? Why it's not, why in this case wouldn't be equivalent? Maybe an ideas. Well, basically because since we presenting our vector like in the space here, we show it already in a kind of sphere. And if I'm having a vector and which is multiple by more than 1, then I would have some changes here. Maybe the vector is going in the other way around, because here it's important to have the sign of this as well. So it's not about only the state of 0 and 1, but it's also, we remember that we have the A of 0 plus B of 1, and if we have the sign, like the sign of them, they could be different. And therefore, I need the 3D sphere, not only a 2D space where I have the 0 and 1 states, but also it's need a 3D space to present the sign. And now let's go back to the measurement and see what is basically in the mathematical way it means. It likes measurement is basically forcing out a state or like a system from being in the quantum state to go back to the classical way. As I said, it's like taking a snapshot of this qubit, which is moving around very quickly, and switching between the states, and I'm forcing at a specific type of moment that it will have a specific value. And here, if I present the value of that I have here, that the square of 2 through to 2 of both states that I have here, they have an equal probability, which means that um, each of the state can be measured equally, or like could have the output in an equal probability. But there are other cases where the probability is different. So here, for example, I have in this example here that the square of 3 to 2 minus half e to the state of 1. And this is basically what we need, because let's say if I want to or like the correct result is the state of 0, not of the state of 1. And here I have a chance of 75% of getting the 0. And this is what actually interference is making. Interference is trying to affect uh, these scalars like the A and B. And in cases of multiple qubits that we have more and more, in order to get out or like to increase and enhance the probability of getting the correct solution. Getting back to the entanglement means that, or like if I have two qubits here I need, because we spoke about two quantum system at least, and they are presented in different combination of their states. Like I have the 0 of 0 and 0 of 1 and 1 0 1 1, which means that, for example, here the first qubit has the value, or like has the state of 0, and the second one has the state of 0, and we need to make sure that we have all combination presented. The A and B and C and D, as we said, they are a complex number, and their norms, or like the sum of their norms, are equal to 1, or like the power, let's say the sum of the powers of their norms are equal to 1. And if they are not 0, like like at least 2 or more than of them are non-zero, and we cannot separate the two qubits from themselves, then they are not independent, and here we have an entanglement state between these two qubits. But what does it mean to separate them? Let's take an example here. I have here this equation of these two qubits, that I have the state of 0 0 with a probability of half, and the other one of also of the 0 1 is also getting a half. So, and the other one would be 0, like would be the norm of it, like the probability of getting 1 0 and 1 1 would be 0. So I can here mathematically take out, or like take out the first qubit, like here take it out of the brackets, and due to the distribution rule here, that I can take it out and say, okay, I can present it in a way that I have the state of 0, and I have here the probability for the second qubit, I have the probability of getting 0 combined with getting the probability of also of a half of the state of 1. And in this case, I'm able to get the two qubits independent from themselves, that the state, or like the behave of the first qubit, is not affecting the second one. If we take another example here, that we have the 0 0 and 1 1, we were not able to extract the first qubit here. We don't have the distribution rules, which means that we cannot split the product of these two qubits, and they are entangled. What does that mean? That if you measured, let's say, the first qubit, which is the first one, and I get a 0, then I will definitely get the value of 0 at the second qubit, because I know that the possibility, or like the state 0 1 is not described here, or like they have a probability of 0. And if I got in the first measurement of the first qubit, I get the value of 1, then I will definitely get the value of 1 in the second qubit. And this is what is meant by the correlation between these two qubits. And the first one, if you measured here the first qubit, then you will get a 0 state, but it doesn't mean that you know what you're going to get by the second qubit. And this is what entanglement basically means. Doing the operations or gates, like In the same way that we have in the classical circuits, we have operations like add, combining with the value, or like the ones from two bits, or like the OR, which takes out one of the bits of 2 bits, or like the NOT, which is the flip, as we saw it here. We have also the quantum circuit. Since we are dealing with vectors, then it's not about dealing out or like putting out one number, or like here we are talking about a two-dimensional space in the complex number word. So we need here a kind of matrix that applied to these vectors, and we will call them reversible gates that could be applied to 1, 2, or more qubits. So basically the qubit gate would be 2 by 2 matrix, which is reversible, means that you can undo the operation. If you defined out an operation that is irreversible, then this won't be qualified to be a quantum gate. And the problem is that we have also the errors that might happening during making out some operations. And these errors are caused of the noises of the system that is interacting with our quantum system. And these noises could be also described as kind of operations. So if some of the noises might cause flipping the value of the state, or like flipping the state of the qubit, um, or like maybe making some control, or like making some XOR with the qubits. So it's also important that we have also errors that is be described in the quantum circuits also as kind of quantum gates or operations. Let's get back to the last phenomenon, which is interference. We have 3 qubits, and these are the combinations of all these states, like starting from 000 to reaching out 111. And by the default, they would have all the same probability, which would be the eighth. Like if you measured one, then you would have the probability of getting 101, for example, as an eighth. But this is the problem. What it say if I need to extract, for example, the 101, what can I do here? Let's try it maybe to flip it out. Like it would have a negative value. Like here's the amplitude won't be affected because you are going to have the norm, and the norm will remove out the sign. But then I would have for the scalar a negative value, which makes it unique than other states that I have. Or I can enhance the probability of it and makes it different. And in this case, so that means that doing out a measurement on this quantum system will let me get 101 with a probability of 0 or like 80%, and getting out any other results would be around 20%. How I could benefit from this? We won't use quantum computers to solve out a problem, and then I don't know what results I might get. I need a specific solution. Let's say if I'm looking out, like if I know what is the solution here, I would say, okay, that's easy. I will enhance the amplitude of the 101 in order to get out, at most cases, the desired solution that I want. But actually, in the real use cases, you don't know the solution. Otherwise, you won't solve out the problem at all. But what we know, it's already the characteristics of the solution. And the optimal solution, for example, we know that the derivatives of the function at the optimal value would be equal 0. So you basically look out between of these values, which one has the derivative of 0, and then you amplify its amplitude, and then you can calculate the solution, or like then you will know what is the solution. Here we have a similar way, and this is the idea of the quantum algorithms, what they do in order to enhance or like to get out the correct results. Maybe before I jump in, is there any questions so far? Feel free also to write it in the chat if you don't want to speak. Okay, then I will do again. So let's get back to the real use case. I have the coffee, which I'm drinking right now, and let's say that we need to simulate the chemical interaction which is happening in the caffeine. The caffeine is a molecule that is already defined the components of it, and I need to simulate its interactions with other chemical materials for different use cases. Well, actually, for this with the classical computers, you need approximately 10 to 48 bits to present this energy configuration of a single caffeine molecule. What does that mean of this number? This means this is about or like around 1 to 10% of total number of atoms in the Earth at all. But with the quantum computers, how much do you need? Well, the answer would be approximately you need 160 logical qubits, which seems very realistic or like very near from the realistic to use. But it's also important to mention that we won't replace the classical computers completely. Think about your last vacation. You would go out from your home and then maybe take a taxi to the airport. And then from the airport, you will get a plane in order to reach out the other country. And from there, you will get out a taxi to reach out your final destination. The question is, would it be suitable or realistic to take out the taxi from home and to travel to the other country to reach out your final destination? No. The other question is, would you take out a plane from your home directly to the airport? You would say, no, this is not productive at all. This is just wasting of energy. And this is wasting of resources. So therefore, you use out the taxi in cases would you know that, okay, I don't need to use any superpower to reach out the airport, but for there, I need another tool which let me reach out the final destination that I want. And this is what is quantum computing is going to do. We saw that we need already to transform the information in a way from classical way, from the encoding way that we've been doing, and feed it out in the quantum computers, which might cut out the computing time or like the traveling time from years to hours, and then decode these results and bringing it up again into the useful information that I have. And in this way, I'm able to describe or like discover new use cases. So basically, I would have two tools. The classical computers, which are well suited for many problems, and the new powerful tool, which is the quantum computers that let me explore more use cases. Think about it, it's more or less like the spoon and the knife that you have, that each of them have different situations, and you cannot and you should combine them in most of the cases when you eat, but one of them won't replace the other. Although the knife could be, I don't know, more sharp and have more usage, not only in the kitchen maybe, but it won't replace the spoon. So this is the important information that we need to keep in our mind. You might ask, okay, we have now explored quantum computers. When can we use it? Or like when it's the time to jump out from the taxi and get the plane to reach out the final destination? Well, this question is basically explored from something called quantum utility. The quantum utility defines out when the quantum computer is the best platform to run a quantum circuits or a quantum program. We have seen so far that we try to simulate or like to run out these quantum programs, these quantum algorithm on the classical hardware. But when we reach out a point that I'm not able to do it even on the classical chip, whether it's a CPU or a GPU or a high performance computers, and I need to use out the quantum computer, this is what is called the quantum utility. And it's coming out from the utilization of this hardware. This is the first milestone, but then we will come out to the questions. When I need, or like when it's the moment that quantum computer outperform more or less the classical computers. This is what we call the quantum advantage. It is the moment, or like it's not, it's the use case when the quantum computers can solve out a problem more accurate way, or like even a cheaper way, or like even in a time-effective way than the classical computer is doing. This is not only one moment or like one step, but it's kind of hypothesis. That is, we are in IBM are exploring that we take out a use case. We tried out two approaches. One is classical, one is quantum, and then we said, okay, quantum here is outperforming. Then we go back to the classical one and try to select another approach in the classical world, which is outperform the quantum computers. Then we thought, okay, we need to improve the quantum approach in this case. And this is a kind of race that when it ends up that the quantum computers can can outperform all, let's say, the classical approaches that we have for this solution, then we have here a kind of quantum advantage. When did this happen? It already did. In 2023, the IBM and the University of Berkeley have demonstrated through an experiment that when we use out or like when we design a quantum circuits which needs more than 100 quantum qubits, then the classical computers are not be able to perform or like to simulate the workflow of the quantum hardware itself. And this is basically more or less with 127 qubits with more than 2000 gates, and it was outperforming all the classical computations that were trying to simulate the quantum behavior. In the next way, it's not also important about to need when I can use the quantum computers. It's also important for me to know that if the quantum computers are reliable to be used. We have spoken so far and mentioned something called the noisy, which are producing or like affecting the final results that I'm getting and producing out some errors. And in the next year, in 2024, we have discovered a new method for correcting these errors. Even if they're going to happen, I'm not going to prevent them from happening. I'm able to correct them, which let me reduce or like came up 10 years closer by reducing the required number of qubits to solve out a specific problem. And this will comes up with the with our goal right now, that is the quantum advantage. As we see, it's also important not to outperform the classical computers, but also to produce out the reliable result. And it's not only one single moment, it's kind of hypothesis that is be able to be or like the subject to falsification. You can do out one experiment and say, okay, quantum here is producing something good or like something better than classical one, but you need to make sure that you have done all the classical approaches as well. So far, we have established the quantum utility, and in the next year, we're going to demonstrate the quantum advantage. And our next milestone would be in 3 years by delivering the fault tolerant quantum computers, which knows out quantum or like are familiar with the errors that might happen and can be able to correct them. Any questions so far? Then maybe let's dive deeper into quantum applications. Basically, we have 4 types of applications or like categories, let's say, that we solve our problem with them. First of all, the chemistry and materials, trying to design materials, simulating the molecules and interaction of the chemical particles, optimization related to finding out the optimal solution of a specific problem and search for it. The machine learning and AI, it's known already that the machine learnings, yeah, it's a very great tool, but it needs a lot of time to solve out or like to train out these models, which takes out a lot of energies and so on. We can use quantum computers even here, and we have the numerical solution. And this is coming up across different industries, starting from aerospace, designing materials for the aircraft, ending up with healthcare and life science by discovering drugs and making out some simulation and so on. And it's the use case itself could be a combination of these 4 types of problem, like because you might look up for an optimal solution that you need to feed it out in a chemistry simulation in order to get out some good results. One of the most use cases that I would like to talk about is with Credit Motwell, which we started cooperation with them of starting or like from 2016 that we believed on quantum computing to explore, and we explore the use cases mainly in 3 things. First of all, improving out the customer experience, detecting fraud, like detecting something in order to make sure that the transactions in the finance world is safer, and very safe, done safely. And also the risk management, which is about calculating the risk of, I don't know, doing out some portfolio or like doing out some investments and so on. And all of the use cases that we do in cooperation with our clients and partners are being published in our quantum block. And also we have different papers that is being published to the different applications that we have. Shall we now take a small break? I see it's approximately now 40 minutes. Shall we take a small break from 1 or 2 minutes, or do we have some questions, or shall we proceed, Nathan?
We could take a small break. If anyone has any questions, they can raise their hand or put it in the chat.
Yeah,
So we can give like 5 minutes.
yeah, that's cool.
All right. So if anyone has any questions, just raise your hand or put the question in the chat. Okay.
Yes, I just saw the questions. Yeah, there sure there are problems that IBM really has solved. For example, one of the latest problem that we have published was also in the finance world with the HSBC, and they are related of the giving out recommendation related to making investments, like the probability that of more or less the market analysis and the stock markets. And basically, the quantum computers or like the quantum approach was able to produce out better probabilities or like better results that is up to 30% better than what is currently AI and classical computers are doing right now. I would really recommend. There is also a published paper about that publication. I would really recommend reading this again. That's a very good question. Like because mainly because about the let's say the noisiness that we have. We saw that okay, we have defined the concept of the quantum, but there are very challenges that we are getting right now. First of all, the noisiness, like the noisy systems that is interacting with our quantum systems and producing and affecting out the results. Therefore, we trying to outperform this problem with introducing the error correction. The second thing is about the lifetime, let's say, of a qubits. Like we produce out the results in the quantum hardware, this isolated qubits, let's say, but it's also important to know how long I'm able to perform out information before this qubit states would vanish, because it's more or less like an atom or let's say an electrical that is we can keep it for a specific amount of time, then it might be vanishing. And this is also related to the quality of the gates, or like the quality, not of the gates, of the quantum hardware itself, that and it says out in the specification how many gates can you perform in series, for example, with this quantum hardware. Sure, I will go back to the slide, and it's about increasing the amplitude. Yeah, so let's get back here a little bit. So we know that we have, by default, I have an equal probability of getting one of the combination of the states by the default. Like, as I said, I have here 3, or like I have 8 states, then the probability of getting one of them, it's 1 to 8. And then, like, how this is basically done, like if you're familiar with, for example, signal processing, that you're able to enhance one of the amplitudes. Like, just imagine that each one of these states are a signal of itself that has a specific frequency. Basically, they would have the same frequency, so they are overlapping, and you wanted to increase the frequency of one of them to turn it out, for example, from this wave into a wave with higher spins, let's say. And this is what you are doing mathematically with the states, or like you're just enhancing the signal by like increasing the amplitude. Why we are doing that? Because we need, for specific problems, to get or like for problems, we need to get out the real result. Because if I'm solving out, let's say, a search problem, I wanted to search out the 101. And if I'm using out the quantum computers and I know, okay, it's only with probability 1 to 8 that you will get 010, then okay, but this is not reliable. You're looking always to get the desired results that you want. How I can make sure that each time in this kind of quantum probability system that I will get the results that I'm looking for. And therefore, I'm doing the, let's say, the enhancing, or like improving, or like increasing the amplitude of a specific state. Physically, you can do this by performing out, let's say, or like, let's imagine that we have that the qubit, or like these 3 qubits, are moving around, and we know when they reach out a specific state, we will cool the qubit in order to slow down. What does that mean? It means that when it reach out the specific state that I want, it is gonna become very slowly while moving. In this case, when I'm doing the measurement, I'm gonna get with 80% probability the state of 101. And when it reach out the other states, it's gonna move out to the normal speed that it has. Just think about that we have a qubit, or like the qubits are just particles are moving around very quickly between these states, and you wanted to make sure that when I'm doing the screenshot, I'm gonna get these states. I hope that this answered your question. Where do you suggest to get access to public resources that cover quantum models or simulation? We will do this by the end of this webinar. I'm gonna show you out how for our learning platform and some resources that you might be interested in. So maybe I think the 5 minutes are now up, and we can go further. So we have, let's come back to the slides where we were here. Yep. So basically, we have now the quantum hardware, and we would have Qiskit. Why I need Qiskit? Because how can I communicate and deal with these quantum hardwares? In the classical way, you have the programming languages that have been written of, like, I don't know, more than 100 of programming languages in the world that communicate and being translated into the machine language in order to perform our problems. Here you need Qiskit, but it's also important that we don't need quantum to be performant, that I need only to execute the problems and try to execute it with the best timing and the best performance. It should be easy to use, because if I have this wonderful technology that is basically based on a very other type of physics that I'm really not familiar to, I need to understand it quickly in order to make the applications easier. And therefore, what we've done in our quantum platform, we do it in a layer way. So here, for example, we have our quantum computer, which has the quantum processing unit, which is basically the quantum hardware. Qiskit contains like several parts on the different layers that we have here. First of all, we have the Qiskit runtime, which is responsible for communicating directly with the hardware in order to execute out the quantum programs. And then we have the Qiskit serverless. The quantum computers are accessible through the cloud. So it's not something that you will own at home. It's something that you need to access from the cloud. But think about this. If you need to access something from the cloud, then you need to make probably a connection, I don't know, TCP or like an IP and UDP, and maybe preparing out the infrastructure and making sure that the server are connected and so on. Qiskit said, okay, I'm going to offer you serverless, which will let me, as Qiskit, I will take care of these information, and you just only need to perform out or like to focus on your problem, solving out, designing the quantum circuits, and then you will execute the program and I will take care of everything. And how you're going to develop or like build on the quantum circuits, you would going to use it through the SDK. The SDK contains a lot of functions that let you design, which we're going to see later, that you let you design the circuits, execute it, and then maybe make also some optimization, and then finally you will be able to decode the results. It's not only about programmers and developers. We have now made out an extra layer of abstractions where we designed ready functions to use and applications that are familiar or like associated with related use cases that you can directly use them without doing out or like writing out any codes from scratch and directly use them and apply them. It's also important that the quantum computers can be also integrated with high-performance classical computers like the CPU, the GPU, and so on. And Qiskit is able to do this because it has also the interfaces and the integration with high-performance computing. So far, we have already introduced something that's called the code assistant, that the AI will help and enhance the quantum computers. In this case, it's more or less a quantum or like a code generation for you in Qiskit. So Qiskit SDK, this is our software kit. We thought if you need a circuit, then you need Qiskit. You need to design your quantum program, then you need Qiskit. Qiskit is basically not a new programming language, but it's more or less written in Python. So you don't have to learn something new. It's already written in Python. And it shows out that by executing the quantum circuits, like Qiskit is not only designed for IBM Quantum, it can be integrated with 10 different providers, like Azure Quantum, like Ionic, Amazon Braket, and so on. And we saw that in the last year survey of the Unitary Fund, that 70% or like 74% of the developers, their first choice of when they kind of develop in quantum, Qiskit is their first choice. And it's also outperforming other frameworks that we have, or like development kits in the quantum world. Here, for example, we have a speed that measures how long for an SDK to create, manipulate circuits, and transpile them, which means turn them out to a ready hardware solution to be executed in the quantum hardware. And here we saw that Qiskit, for a very, very complex one, it might take out 49 minutes in comparison with TCAT that might need 27 hours. So Qiskit is your first choice. Basically, to solve out a specific problem, we have something that's called the Qiskit pattern. So if you have a problem, let's say, or like we have a use case that we have a client and it says, I need to solve out to your quantum hardware. Then first thing that we do, that we map out the problem instance. We have the components of them. I don't know, we have vehicles, we have timing, we have objects that need to be transformed. We try to map out this problem from its abstractions to quantum components, like quantum qubits or quantum circuits or like operations, what I need, which operations that I need. Then I need to optimize it in order to be ready to be executed through the Qiskit runtime on the hardware. Then I will get out some results probably in 0 and 1, like in bits. I need to decode the results again and post-process it in order to get out the final business solution. Trying to make out in a form of input and output. First of all, I have the mapping problem, which is I have the domain inputs, as we said. We have them as a type of components. And then I'm going to turn them into a quantum circuit that contains the different types of gates that I have and operations and the required number of the qubits. Then I will take the circuits and we'll do the transpiling by turning into, since we have, or like each quantum hardware has a different architecture, then we need to make sure that these circuits are also mapped to the, or are like optimized to be executed on the hardware itself. Therefore, we get the ESA circuit. And this ESA circuit then could be directly executed on the quantum hardware, and then we get the values, the expectation values or the samples. We will talk them later, what is the difference between an estimator or like a sample. Then we will get out the results from the samples or like an expectation, and we'll try to either decode it again or like into the data objects that I have, which is the domain inputs, or like to make some visualization and making out some charts in order to see the statistics and so on. So we have the quantum software written in Qiskit and done in QViews, and then we will get our useful work. We will jump now to a notebook that we're going to do together and see how kind of things are integrated into the, or like how to run out and design a quantum circuits and run it on the IBM quantum platform. For just for note, like if you have an access or like the free access on the quantum or like on IBM quantum platform gives you 10 minutes each month freely to be used on the quantum hardware. So let's get back here and I'm going to open my Qiskit hands-on, and this is like the first thing that I'm going to do. I'm going to install Qiskit. So as we said, Qiskit, it's the SDK that contains of the runtime service and the functions and different type of operation that I have. Installing Qiskit, it's very, very easy since it's kind of a framework or library written in Python. All what you need that to make sure that you install it through pip. Here, for example, I'm using the Jupyter Notebook in order to make out my own environment and not installing this globally on my device. And then here I'm running the command of installing Qiskit. We have different, it's not only one thing that you will install. We have like the Qiskit IBM runtime, which is relevant to connect with the IBM quantum hardware. And we have the overall Qiskit, and we have also this Qiskit Air, which is related for simulators because we don't have only execution on the real quantum hardware. We can also instead doing simulations, as we saw already what classical computers have been trying to do. So therefore we have the AAR quantum simulator. So we're going to install this, which I've already done, and that's therefore already the requirements I have. So there is no problems here. And then I'm going to go back to import Qiskit and making sure that the Qiskit version that I have is already installed. Now we are in Qiskit version 2.2, or like we have now the Qiskit 2. Setting up with the cloud account, probably like in order to get access or like to integrate your program and be able to run it directly on the quantum hardware, you need a kind of API key that is being generated from your account on the IBM Quantum platform. Here, for example, I'm gonna log in here with my account and doing out. This is my by selecting the region, of course, and then it's gonna log into my here. This is, for example, since I have VMers, I need to make out some internal login. But for you, maybe this window will not be shown on if you have an external account. Then when you land on the page of the IBM Quantum platform, here you see that I've already, for example, used this instance in order to make sure that I'm using out my 10 minutes on the hardware. I need here to create an instance. And after I create it and can here, I create a new API. And then I can type in a specific name. I don't know, Qiskit Fast 2, for example, and then I'm going to go create, and then I need to copy this. And when I can copy it, I will come up here, and by initializing my Qiskit runtime service, I need to save out the account. I call here the method to save out the account, which says, okay, the channel is IBM Cloud. I'm using the IBM Cloud, not another provider. And here I'm going to use my API key, and here it's the instance that I have, which is in this case, you can copy it from here. And this is relevant to on which how do you yeah, it's basically on which instance that have you created, and in order to take out the name of it. And here, for as I said, I have a 10 minutes free this month. I have probably used 10 seconds of them already, so I can use again the rest of them. Then I will go back to my Qiskit hands-on here. And then I need to make sure that I have the connection. And this is when I'm initializing a new object, or like I will call it here a service from the Qiskit runtime services. And this is the save account of it. And I'll click here. Sorry, I need to define here again this one. And then I'll call out this. So you see here the information has been printed out. This is the URL that I'm using. This is the Cloud IBM platform. And this is the token that I have that is being generated for me to use, and using out the instance verification. It's also important, and it's not a private endpoint. And then I'm going to see which backends I have, or like which IBM hardware I'm going to using. And this is shown up here that this is the IBM backend Brisbane, or like the IBM backend IBM Torino. So also for the free plan, there are specific types of, or like not specific arts or like names of quantum hardware that is available from IBM to be executed on. Not only the IBM quantum hardwares are available for publics, some of them are dedicated to clients and researchers to do specific researchers on. Here I'm gonna first design my first quantum circuits, let's say. And first of all, I need to import, or like make sure I've imported here everything. Starting out from Qiskit, I will import the quantum circuit object, which is basically, or like the class quantum circuit, which is basically implementing the object of quantum circuits. That includes qubits as well as the operations on it. And here for information, in order to visualize my information, I will use out the state vector. And for visualization, also, I'm going to use the plotting states Q sphere, which takes out the input of the qubit and trying to put this out in a visualization form of the 3D sphere that we have already seen. This is the simulation. I've already done this. And this is the Qiskit runtime servers and the sampler in order to calculate the results, which is relevant for the results, and the transpiler, which is also responsible for mapping out my quantum circuits into the one for to execute it on the hardware. And here I have the NumPy in order to import the squirt functions. So importing this, and then we will start by our first qubit. I have here a qubit, which is a state of the 0 and 1. And here I'm going to represent it instead of A and B. I'm going to represent it in a related or correlated form that I have, okay, if I have the state of 1, then I have the probability P. And in this case, the other probability, due to the rule of that the sum of all probabilities equals 1, then this means that the probability of 0 would be the square of 1 minus P. And yeah, in this case, I'm gonna visualize it, and starting out by making out some visualization on the 3D sphere. And here I visualize the state, or like the state 0 on the 3D sphere. And it shows me out that the vector of the state 0, which is the one which is lining up in an vertical way. And here I'm defining phases, or like this is important for me to remind me with the angels that here I have 90 degrees, 180 degrees, and 360 and 270 degrees, and here it's 0 or 36 degrees, which is be a 2p. Then I'm going to design a quantum circuit. How to design a quantum circuit? Already you initialize an object. I will call it here QC1. and the quantum circuits. The first and default input here defines out how many qubits you need. And in this case, I need only 1 qubit. Then what I'm going to do, I'm going to make out a state vector of this quantum circuits in order to plot it also in the 3D sphere. And here I'm getting a similar results because by default, all the state, or like all the vectors will be in the 0 state. Now let's do the other way around. Let's visualize the 1 state. And this could be done when here I'm taking out the state vector and making out a combination of them. And by doing this, then I would see here that here I have a vector which is also in the state of 1. And here, if I need now, maybe let's say the combination of them, like with a probability of 1 to, of like of half of each one of them, I will visualize it here, and I see here that now it's now like in a different color, because it's basically presenting that this is the state of 1 and this is the state of 0. So now let's get started with manipulating the qubits. The qubits, we need now to apply some quantum gates. And we have already defined or like known 2 type of gates that we have. First of all, the X gate, which is the gates of flips that flips between the states of 0 and 1. So if you have a determined state of 0, then you will get 1. And if you have a combination of them, it will flip out the probabilities of them. And the H gate, which is also the Hadamard gate, that this present or like this transform the classical states into quantum superposition states by, for example, the state of 0, it's going to form it of the half of 0 plus half of 1, which is known here is the plus vector or like the plus state. And we have, this is, for example, the Hadamard gate. And for sure, we have also different problems. And if we're dealing out with the 3D sphere, then we can think about the quantum operations as they are kind of rotations that is being done on the vector of this 3D spheres, and each operation turns out or like make a transformation or like a rotation of the vector into another point on the surface of this sphere. For example, here we're starting out by the state of 0 and we are applying the Hadamard matrix. Then we saw out that we have like the 0 and the state of 1. And or like and the other way around, if we applied the X gate, then we have the flip it. And then if we applied to the flipped one, if we apply the Hadamard gate, then we will get out the sign in another way, because here you applied the flip at 1, you applied the Hadamard to the state of 1. And here we have, for example, the S that is, for example, doing also some rotation in a way between the states, let's say. Yeah, and we have also, for example, the Z operation, which is doing also a shifting phase and so on. The Z means like I'm adding a phase of 180 degree, for example. So in this case, like if you have the 0 and 1, I'm going to phase them, which means I'm going to rotate both vectors in a way that the 0 would take the place of 1 and the 1 would take out the place of 0. And here the S would be also doing out a phase of 90 degree, or like the S dagger of it, which applies the subtraction of a phase of 90 degrees. So these are the basic operations that let me process information in our quantum world. And how I'm going to use it, or like how and I call the method, basically, if you have the quantum circuits and you wanted to apply one of these methods to the quantum qubits, then you just call it as a method and you give in the parameter, the index of the qubit that you wanted to apply the operation to it. So for example, here I wanted to flip the first qubit, or make a bit and phase flip, or like a phase flip, or like doing out in a superposition, or like a rotation by 90 degrees, or like a rotation by minus 90 degrees. So let's get started. We are going to design a circuit that flips out is to reach out the state of 1, starting from the state of 0. So here it's my code. I have here the quantum circuit, which includes only one qubit, and I need to flip it from 0 to 1. Basically, what I'm going to do is basically defining out the flip operation here, and I'm going to say that the QC, I'm going to apply the flip on the first qubit, and then I'm going to check out the solution. So yeah, as I said, here when I visualize the information that I see here, it's now on the 1, or like in the states. And in order to make sure that my code is doing something, here just comment my operation that have been done so far, and then checks out, okay, now it's now initialized again on the state of 0. And when I apply my information, then it's going to be flipped out. Maybe a questions in this case. How about if I'm gonna put out maybe here another index? What's gonna happen? Let's say, and here you're gonna get an error because you defined already the quantum circuit with one qubit only, and then you said, okay, I'm gonna apply it on the second qubit because the indexing is starting from 0. Then you're gonna get an error. But maybe if we applied, let's say, quantum circuits on or like defined one on a qubit and 2 qubits, what I'm gonna get here? Let's maybe get a try here. So as you see, I am having 2 qubits, and then I said, which is basically 0, 0, 0, 1, 1, 0, and 1, 1. And then I said, I'm going to flip the first qubit, flip the second qubit. Then what I'm going to get here is maybe 1, 0. So this is basically what we've done. But if I'm going to do this again, let me try it again here. Yeah, you will get also the same result. So this is basically flipping. And here let's maybe now create let's jump out to the next exercise by creating a superposition. Mainly that we are creating this plus vector, which is basically the probability, or like the 1 to the square of 2 to 0 to the state of 0 plus the state of 1. So what I'm going to do here, basically applying the Hadamard operation. And this is basically by applying h to the first qubit here, and then as I said, I'm going to get here the superposition of the two states that I have. And in a similar way, if I wanted to reach out the minus sign, which is basically here have a minus of the state 1, what I'm going to do here is basically QC. I'm going to first of all apply apply the flip, and then I'm going to apply the Hadamard again. So let's see now if we get the results, and here it is. So I'm able now to get that the state of vector of 1, it's on 180 degree, which means it has a minus, and we have the 0 state, which is the vector of 0, 0. The point is, and my question would be, why I did it in XH type? Why I did it? Can I just not flip it out or like switch between the two operations? Should I not get the same results in the end? A question. Maybe let's try it out. Like if I get now the H, like applying Hadamard at the first point, and then I'm gonna flip. What's gonna happen here? I'm getting the result as it would be only in Hadamard. But why? Because basically when you apply the Hadamard matrix, then you will get out this plus sign, this plus vector. And then you're gonna say, okay, I'm gonna flip between the A and B of the state of 0 and state of 1. And basically both of them have the plus sign and have the same number. So flipping them will be shown as there was no effect done by the flipping, because you have the same probability of both of them. Therefore, you need first of all to apply the X and then to apply the H. Please make sure that in some cases, or like not in all the cases by default, that the operations can be switched between each other. Now I'm going to jump over maybe to the quantum case with maybe multiple qubits, and then you might help me out. So for multiple qubits, if I'm going to do operations on multiple qubits, then I have here three interesting operations that I have. I have the controlled C, which has the input of 2 qubits, the C and T, And basically it says, okay, if the first qubit, which is the control qubit, is 0, then do nothing with the target qubit. But if the control qubit is 1, which is a positive sign, I will flip the other qubit, let's say. The Z gate works in a similar way, that if the control qubit has the value of 1, this means I'm going to do the operation, which is the phasing, or like doing the phase on the qubit T. The swap is basically switching between the state of A and B. So maybe let's get started with this Bell state, which is a little bit interesting. We have two states only, but we have now two qubits, the 0, 0 and 1 of on. And both of them have the probability of half. So how we can construct this? Any ideas? Feel free also to write in the chat as well. So maybe first of all, we have now a quantum circuit of 2 qubits, and these 2 qubits are in the 0 state. What we're going to do, first of all, we need to apply the Hadamard matrix of the first one. So like now by applying the Q, C, Hadamard operation on the first qubit. In this case, I'm going to get out the Hadamard state, or like the combination, or like of the 0 and 1 for the first qubit, which means that I would have half, or like 1 to the square root of 0 plus 1 to the square root of 1, and these are like in a kind of brackets multiplied with the state of 1. Maybe let's get try to write this out in a kind of notebook. Let me just open this and get some notebook here in order to understand what we are doing here. Okay, it's not working. Hmm. Maybe let's try that. Oh, solutions. Yeah, technology is always a little bit noisy. Okay, so maybe let's get this. So now we have the text of, like, now we have two states, as we said, which is in 0, 0. And let's get this a little bit bigger. Next here. Okay, so now I need to switch it to the state that I want, which is 1 through square of 2. And here between the states of 0, 0 plus 1, 1. So I think I'm right. Yes. Yes. So we'll make this bigger a little bit. So first of all, I'm going to take this first qubit and then apply the H operation on it. So in this case, I would take out this and then making out the H on it. This would result in that I have here the 1 through t of 2. And then I'm going to have here, for the first qubit only, the two states which I have, which is the 0. I'm going to remove here the brackets just to show that for the first state. Like I will have a superposition of the state number 1, and with the next qubit, it will be state of 0. So now I'm going to take out this, and let's see what is here the problem. So if I have a 0, then the next one should be 0. And if I have a 1, then I should flip out the value of this second state. So what I'm going to do here, so this is basically, it's basically a controlled knot. So if you applied now a C knot on the whole quantum system, then you will get out this final result. Because in this case, it would be that, okay, the first qubit is 0, then I'm going to leave out the second qubit, but in the second time it would be a 1. So that's why I'm going to flip it out. So let's take this out, and then it means that I'm going to apply a QC CX on 0, and the target qubit would be 1. So it's going to try this, and therefore you're going to get, this is the probabilities of the, or like the combination between or like let's say that the probability of the different combinations, that for 0 0 you're gonna have, but for the 1 0 and 1 and 0 1 you're gonna get nothing because the probability is 0, and for 1 1 you will get also the other half. And this is how it's gonna describe our quantum circuits. And basically, if we wanted to visualize the circuit itself, how it's gonna shown on different lines that you see here, okay, that the first operator is the H operator, and then I'm gonna apply the controlled knot that this, like the flipping would be done here on the second qubit. On the first qubit would be the controlled qubit. Let's construct this state, for example, which is half, or like which is the combination of 0 1 and 1 0. What would be the case here? Actually, let's maybe try to make a similar case. First of all, I'm going to apply the Hadamard on the first qubit. So in this case, you will get 0 and 1 of the first two qubits. But then I need to see that that here I have something in another way around, because here I have, it's not about that if the first qubit is 0, then I should flip out the next one. And if the first qubit is 1, then I should do nothing. This is more or less similar to the controlled knot, but it's the other way around. And in order to apply this, so this means I need to flip out the first qubit. So I'm going to flip out the first qubit again, and then apply controlled knot. And then let's contract. Let's see this. So here I got something that seems to be same as what we got. Maybe someone could tell us why. Because first of all, here we mentioned that we're gonna do the X on not on the first qubit, which is not true. Actually, we need to flip out the next qubit, because if you flip out the controlled one, then you have the problem by controlling out the source. Therefore, you need to flip out the second qubit by saying, okay, I have now the 0, because, or like if I have the state of 0 in the first qubit, then leave the second qubit. But if you have a 0, or like if you have the state of 1, then please flip the second qubit. Therefore, we need to apply the flip on the second qubit, not on the first one. So now I have a little bit advantage that now I can represent the two states, which is the 0 1 and 1 0. But here we have a problem. Like in the Bell states that I've defined here, there's a minus of the 1 0. So I still need to do something. That is basically, I need on the second qubit, I need to apply a kind of shifting in the other round, and therefore I need to apply Z operation on the second qubit. And then, therefore, we got it. Here it is. So now I have now the desired result of this Bell state that for the 0, 1, I have, for the 0, 1, I have the probability of half, but 1, 0, I have the 100, for the 180 degree. And this is basically how it's going to look like. And yeah, there are also these problems that, for example, here we have that we have quantum circuits described in this function below, and we need to swipe out the states of the first qubits and the second qubit of this one, which means that I need to do a swap operation. And how can we do this? Basically by performing out an Rx operation. Because here we have already defined quantum circuits that the first one is doing out a rotation x by the degree on the first qubit, and then I'm flipping out the second qubit. And what I need to, let's say, more or less do a little bit something similar. And this would be done by, I think it's already solved. I think so. Yeah. Okay. Let's just skip this part. Yep. This is already solved. Sorry. Yeah. But maybe let's take out this GHz, which is on 3 qubits. And in order to illustrate this 3 qubits here, which is only of the states, either it's all of them are zeros or all of them are ones. And here, this is also important for the solution part, because here I'm having a kind of an attribute of the solutions that or like of the states that I want to have, that all the qubits must be in the same state and all other combinations that I would refuse. So how to construct this is basically I will always like starting out by a Hadamard matrix on the first qubit, and then I would have the combination of 0 and 1. And the other 2 qubits will be state, or like currently will be on the state of 0, both of them. So I need to flip out the first, the second qubit based on the control of the first qubit, and also then afterwards to do also a controlled a C naught between the second and the third qubit. So I'm going to do here a CX between the first and the second one, and then I will do a C naught between the second one and the third one. And therefore, I'm going to get my results here. But here I have a problem here, I think. Yeah, I just forget to initialize the quantum circuit itself. So I'm going to do here quantum circuit just also equals to 3. So now let's get started. It's not defined. I have a typo. Okay, now it's look good. So now I have this, that I have now the 8 combinations of the different states that I have, but I have only the probability of getting 0, 0, 0, or like the combination of getting 1, 1, 1. And this is basically getting out by applying the Hadamard matrix. So always start with applying the Hadamard operation if you are confused, and then trying to find out how to control and affect the qubits between each other. So far, we designed now our circuits, and now it's time to do the optimization. On execution levels, we have 2 types of execution. First of all, the sampler, since we have already seen that we are doing, or like we are now in a world of probabilities, in order to make sure that we are getting the most reliable results, we do some sharding. And this is actually by reapplying or like re-executing the operations a set of times, maybe thousands of times, and then based on the statistical results, you can rely on the results that you got in the end. And this is going to be done by a sampler, which gets the output of the execution of the quantum circuits and basically counts how much per shots you do, or like for each measurement for the shots that you already did. For example, if you said I have a quantum circuit that I will execute 1,000 of time, how much times for each value I'm going to get? So for example, you get 500 for the state of 1 or 500 for the state of 0. The estimator, on the other way around, it computes more or less an expectation that you have one or more value with respect to each state, and this is more or less they are consisting of the expectation value, how much to expect that this value I'm going to get with the standard errors, because here we are doing our errors, and this is more or less related to the um, error mitigations method. So now I'm gonna try to optimize, or like try to make out some measurement to the last quantum circuits that I've done here. And here I'm doing out, the circuit is not defined here. Maybe I have a problem. Let me check. Ah, I have not defined what kind of quantum circuits that I need to apply. And therefore, I'm gonna have for the quantum circuits, I'm gonna have all quantum circuits that I've already designed. I'm gonna make a measurement for them, like the QC1 and QC2, QC3, and QC4. For example, here QC5. So let's now do the measurement of all of them and then add the measurement, or like the running, into this pass manager in order to make some optimization associated with the backend that I've already defined. So now we have done something. QC5 is not defined. Maybe I've not defined this. Let's try to this again. Okay, so now it's applied for the first quantum circuits, or like for the first 4 quantum circuits that I've already done. Now it's time for the execution. I'm going to define a job. Like here I have the sampler that I've already defined associated with the backend that I have. And then I'm going to run this job and print out its job ID in order to check the status of it. And maybe I guess I can see it also in the quantum platform. It's already now queued, so it's now waiting for the execution. Maybe if we here check that which jobs I've already done, I'm getting to the dashboard again. Yes, you can see here that this is the job and this is the status still in pending. So I have to wait a little bit until it's being executed on this IBM Torino, which has more or less 412 jobs. Now it's in progress. It's starting to be executed. And let's see when it's completed. Making a refresh here. Still in progress. Oh, let's take a little bit of time, because it's also important to know that the timing is not only means that this is the time of running out the quantum on the quantum hardware. It's also that I've taken the job from the cloud. I need to prepare it to be fed in the quantum hardware, execute the result, and then produce out the results. So it's not only the timing that is being running on the quantum hardware, on the real quantum hardware itself, and then putting this out in the job queue again. So therefore, maybe it takes a little bit of time. And in the end, it shows out how much time did we need for each job that we have executed. And I think also you can also here make, for example, here, if we can make a job status, then you're also able to see the job status here as well. Now it's done. Okay, it's cool. Maybe it's now not synchronized here. Oh, now it's completed, and it takes out 6 seconds in order to be executed. Then we will print out the results of the job. Or like I'm going to save it to this object in order to make a post process. The post processing, I'm going to visualize what I get. So this is basically counting on okay, in a range of, okay, I need here maybe to pass it to 4. Yep, because I've already only 4 circuits. not 9. I have to just adjust this from the previous tutorial. And then I have made a count of each quantum circuits that I have. So here, for example, for the single qubit states was are the QC1 and QC2. Let's get started here. We saw that for the QC number 1, how probability you will get the results, and it's the probability, or like most probably of the you will get the state of 1, or like you get the state of 0, sorry, and with very, very, very little amount, or like a very low probability, which is 0.001, you will get the probability of 1. You might ask why? Because we have only defined, or like we have only a determined state, which was only, like, for example, the 0, and we made a flip. This is because of the noise, what we already talked about. So although we have only a simple operation, it could be affected by the noise. By the quantum circuits too, where we have two states, or like we have the C naught, we have, for example, that with a very, very little number, you will get the state of 0, 0, but we will get of the 0 of the state 1, 0 with 90% of the times. So I guess I'm going to plot here the other one as well, which is the quantum circuit 3 and 4. Let's see this. Quants all 2, 3. Okay. Gonna remove this, I think. Yep, this is it. And this is the result of the quantum circuits 3 and 4. And if you notice that if we execute it again, we might be able to get out another result. Let's maybe do this. We'll do another time. I will execute it here again. And then again. And here I'm gonna execute another job. Let's see. Now it's a new job here. And it might take out some time. And let's get to see the job status. Still in queued. Yep, as expected. Let's see this again. Still in pending. Yeah, we have a lot of pressure on on our quantum computers around the world. Approximately, we have, I think, 11 quantum systems worldwide, 2 in Europe, which most recently, I think yesterday or 2 days ago, was opened in Spain. The previous one was in Germany. They are still working for sure. And there are also a lot of quantum systems. For example, we have one in Japan. Many of them are in the USA as well. So, and this one, what we are using currently, is in Torino. Maybe let's get this again. And this job status is still queued. That takes a little bit of time. Okay. So yeah, this is basically that's all of the tutorial that we might get. I think this is the last step that we're going to talk about. I just wanted to show you that in cases of re-executing the experiment, you might get out also a different distribution. Anyways, we might come to this back later on. I'm gonna so what's next? We have now learned about quantum, and now we need to get hands-on, more hands-on. What we're gonna do? We have our IBM Quantum Learning Platform, and there's a lot of courses that you might be interested in. starting from the foundations. If you have no idea about quantum computing and so on, you can start with the fundamentals of quantum information, the fundamentals of quantum algorithms, what we get today a little bit. And if you have more focused topics, for example, quantum machine learning or like utility scale quantum computing, where you need to know, okay, what is the level of utility scale? What is, for example, here, doing quantum chemistry with the variational quantum computing. For example, this we have a large platform. And yeah, for example, we have the quantum challenge each year that people comes up and try to start to solve out a specific problem in Qiskit. And we have also a course for it, for example. And yeah, it's opening the link. I don't know why. Yeah, if you wanted to register, it's probably, I think, in the summer most of the time. Um, yeah. And then here, I think if we jump, yeah, here we have the different sources that we have. Okay, we have now learned that we have the IBM Quantum Learnings, but we have also the Qiskit Summer School where people, or like this is an annual event, also providing online lectures that is being delivered by IBM Quantum experts, and you have the chance to ask questions and to engage with it. Also, we have our YouTube channel, which has a lot of interesting lessons about quantum computers. If you're looking out to more credits or like kind of certification, then we have our Qiskit developer certification, which is basically after passing the exam, you will get a certification that you are a Qiskit developer, which is basically covers the basics of programming with Qiskits. And there's also the Qiskit Advocates, where this is a program that you can engage more and more as a Qiskit now expert or like a developer certified in the Qiskit community. And then you can change experience and make some contribution to the Qiskit community itself. Like the summer school, as we said, we have a very large number last year, for example, more than 6,000 seats that has been sold out. We have also the Fall Fest. Thank you so much for attending today. And we have also summer internship. If you are looking to join out our platform, we have a lot of opportunities in doing out an internship in the field of IBM Quantum. The applications open usually in fall and continue to winter for different roles globally. So maybe you are going to be an internship on solving out different problems. Maybe it could be related to the software of Qiskit itself, it could be related to the hardware and so on, or it could be related more or less to the infrastructure. The certification, as we have talked about, there are already more than 1,000 people around the world who has already the Qiskit certification. So it's really a good, or like I think it's a good benchmark in the industry for those who are looking to be identified and being more known as a developer and expert in the quantum world. The Qiskit program, where you can engage with people from different countries in advancing the quantum education and community, making out some contributions, sharing out the knowledge. There are also a lot of events that you can share, networking and doing quantum search and more. And this is perfect for everyone. It's not exclusive about, for example, for specific researchers or educators. It's also be suitable for students, for developers, anyone who is interested to be an Qiskit advocate. It's also welcome. If you're gonna get started, then you can register. Like the applications also open in the mid of the year. And what you need to have, you need just to have some interested in the quantum world or the quantum world worldwide. Basically, or like recommended, is to complete out some of the basics courses in our IBM Quantum Learning platform. For example, mainly the basics of quantum information, which is already for free. And then you register here by this QR code and here when the applications are open. Basically, there are different badges now or tiers for Qiskit Advocate, and each one of them, basically, it depends on how many engagement you have done so far in the Qiskit community. And for example, if you get the tier 1, then you're going to get some special badges where, for example, your name is being shared and so on. Tier 2 and tier 3 is more or less for advanced exportation. And the first step would be the Qiskit Advocate would be the blue badge, I think, which you're gonna start with. So that's it, basically. Thank you so much for attending today. I hope it was not a very, very long session, and I hope that you get a little bit of useful information and maybe fun of that. And if you have still also have some questions, feel free to write me in the chat. And yeah, this is basically your question, Lily. So basic or like IBM has already a lot of resources that you can get from starting out from implementing with the basics, or like learning out the basics of Qiskit, reaching out to how to apply it to a real world problem, like an optimization problem, or like a chemistry simulation, or like there's also a course that is really, really interesting, which is the quantum machine learning for people interested in doing out quantum in machine learning methods. Thank you.